What are the basic concepts of calculus? A lot of the work you do in calculus centers around studying curves. We see curves in a lot of graphs when we look at functions, and there are a lot of curve shapes in real life. Being able to work with these situations requires a mathematical understanding of the structure and properties of a curve, which is the core of calculus. Throughout calculus, we examine as many aspects of curves as we can, but we're going to be focusing on just two major concepts for this class: the slope of a curved line and the area of a shape formed under a curve. One question we seek to answer with calculus is, what is the slope of a curve? When we normally talk about slope, phrases like rise over run, change in y over change in x, or maybe some semblance of how far up and over between points may pop into your head. These phrases all relate to the slope of a linear equation, which is a great place to start. The slope of a line is the ratio of vertical to horizontal change in position. This ratio is constant, meaning that the slope of a line never changes between 2 points. While this is convenient, it doesn't apply very accurately to real-life situations that involve some sort of change in relation to something else. Let's say we have a car that left home and drove 300 miles over the course of 5 hours. If you were to make the simplest representation of the driver's distance from home, you would graph a line from 0, 0 down to 5 and 300, which would be the equation y equals 60x, or maybe more specifically d equals 60t, because we're talking about distance over time. The slope in this situation represents the change in distance over the change in time, 300 divided by 5 equals 60, which we call velocity. More specifically, this slope represents average velocity, since in the real world, a car's velocity changes constantly. Even if you keep your foot as steady as possible on the gas pedal, your car is constantly gaining and losing little bits of velocity at every microsecond. Is it even possible to properly model this situation with a graph? If velocity and slope are rates of change, how can we record those for a function where the slope, or the velocity, is constantly changing? We'll keep this question in mind while we do a little bit more work surrounding linear equations. Here's an interesting idea. What would the graph of the car's average velocity look like in the previous scenario? Since average velocity is a constant rate of change, the velocity would have a slope of 0 and a y-intercept of 60, which creates a constant linear equation through the point v equals 60. We're switching to v because this is velocity now. Believe it or not, these graphs actually have all the same information on them, just in different places. In this scenario, the pieces of information we have are 5 hours of driving, 60 miles per hour average velocity, and 300 total miles traveled. On the distance graph, the 5 hours and the 300 miles are indicated by the last coordinate on the graph, while the average velocity is shown through the slope of the line. On the velocity graph, we can see the average velocity in the y value of the graph, but what about the total time and distance traveled? Well, let's go over to t equals 5 on the velocity graph and draw a vertical line from the graph down to the x-axis. This forms a rectangle with the graph, the x-axis, the y-axis, and our line at t equals 5 making up the 4 sides. As we know, we can find the area of this rectangle by multiplying its length and width. 5 times 60 equals 300. What we discover is if we find the area of a shape formed by the graph, x-axis, and the starting and ending times, we'll end up with the total distance the object traveled in the selected time frame. This might shed a little light on why our other area of focus in calculus is area under a curve. The concept appears to be linked to the slope of a curve. Let's expand on this idea a bit. Here we have what is called a piecewise function. A piecewise function is a single function technically, but it is made up of multiple other functions, each with a restricted, non-overlapping domain. The result is a graph with several segments of graphs that form a single image. The graphs can be connected, or they don't have to be. It's not a specific requirement, but for this case they are. Piecewise graphs allow us to create a more complex situation. For instance, we could now have a person leave home and drive both away and back towards their home by combining linear equations in different directions. Here's someone who drove at 30 miles per hour for 2 hours away from home, 50 miles an hour for 30 minutes back towards home, stopped for 3 hours, then drove at 40 miles per hour for 2.5 hours away from their home. This is neat, But the value here is in our ability to analyze this graph and reach new conclusions. For instance, just like before, what would the velocity graph of this distance graph end up looking like? Since all linear equations have constant slope, and velocity is the slope of distance, each velocity equation will be a constant linear, which is a line that's just placed at the y value of the original equation's slope. This means that we're going to get our series of flat lines, one at 30, one at -50, one at 0 for the time we were stopped, and one at 40. A few things stick out here. First, our second line is negative, which means it represents negative velocity. Interestingly enough, the original distance didn't show any signs of slowing down during this period, as the velocity remained constant throughout. In fact, the only difference between that line and the two lines with positive slopes is that this equation represents movements back toward home, which is the opposite direction of the other two functions. From this, we can conclude that negative velocity is not slowing down, but moving in the opposite direction. Opposite, of course, being relative, but in this case it means, towards home. Next, let's try applying our area theory to the velocity graph here. The four equations make rectangles with areas of 60, -25, 0, and 100. If we add this up, we get a total distance traveled of 135 miles. If we look at the distance graph, we'll see that our endpoint is 8, 135, so this lines up with our previous theory about these two things being linked. While this is cool, it wouldn't actually be quite right to call this number the total distance traveled. Instead, we would consider this number the displacement of the car, or how far away it ultimately ended up from home at the end of the drive. If we regard the distance towards home as positive instead of negative by taking its absolute value, then the total distance the car traveled is actually 185 miles, which we would also get if we made our second velocity positive as well. So we can amend our previous statement a little and say that the area of velocity represents total distance on single function graphs and displacement on piecewise graphs. To summarize these ideas a little bit more too, adding up the change in y for each line in a distance function will give you displacement. If you add up the absolute values of those changes, making everything positive instead, you will get the total distance traveled. If you add up the areas for each line in a velocity function, you will get displacement. And if you again turn all the negative areas positive and add those up, you will get total distance traveled. And keep in mind that these can be the exact same answers for two different scenarios in distance and velocity. The final idea to consider here to expand even further is a velocity piecewise function with sloped lines. Namely, what would the corresponding distance graph look like, and what would be the piecewise function for the slopes of the velocity graph? What would they represent? If velocity is increasing or decreasing, it is going through a process that we call acceleration. If velocity is the rate of change of distance, it would stand to reason then that the rate of change of velocity is acceleration. This also means that rates of change can have rates of change. A changing rate of change, if you will. What about the distance graph though? If the velocity is increasing, then the slope between points must be changing as well. It can't be constant anymore. This can only happen with a curved line, where the slope is different at every definable point in the equation. Since curves are a better model for change over time, this reinforces our goal of being able to define the slope of a curve. That means next we will be looking at some curved functions and trying to apply our new knowledge here over there. But for now, let's see if we can work with these linear functions and the concepts of distance, velocity, and a little acceleration. That's all. See you soon.